On a strip of shadow laid across Earth, cameras waited for the sun to blink. Noon became twilight. The corona rose like a white crown. Then the star field near the dark disk shifted by the smallest of angles. A pencil width held a kilometer away. What moved was not the stars. What moved was the path their light took. Space, which we thought was a blank sheet, behaved like warm glass that sags under a weight we cannot lift. From that day forward, straight lines were not a given of the world. They were a choice made by geometry when gravity permitted it. The sky had not changed its mind. It had told us what it had always been. Now darken a quiet room and set a bulb behind two thin slits. Let single quanta of light traverse the gap and land on a screen. Wait long enough and a set of bright and dark bands appears. A printout of possibilities interfering with each other. Install a small detector to learn which slit each quantum used. The stripes melt into a spray. The screen is the same. The light is the same. Only the knowability of the path was altered, yet the picture of reality changed. How can an outcome depend on whether a path could be known at all? Why should the world care about information that no one read? Place these two scenes on the same table, the bent path of starlight and the vanishing stripes of interference, and a deeper contradiction emerges. If mass sculpts the roots through space, then space is not a passive stage. If information about a path sculpts the distribution of hits on a screen, then outcomes are not merely what particles do in secret. Where, then, does the thing we call reality live? In fields and particles alone? Or in the records those fields and particles leave when they collide with something that can keep score? Must the scorekeeper be a person? Or can a surface of glass, a shaker of dust, a pool of water, a rock face, serve as a ledger that does not sleep? A coastline can teach the lesson without equations. A lighthouse turns. Its blade of light walks across swells and fog and cliff. Out at sea, a buoy seems to blink, not because its bulb flickers, but because the light that should have reached you was scattered aside. Move a few steps up the headland and the blink changes. Move inland and it changes again. You do not command the ocean by shifting your stance, yet your location selects the movie you receive. This is not a trick of language. It is a warning that observation is always from somewhere, and somewhere always has rules. The lab whispers a second warning. Open the back of a camera and roll in an unexposed strip. The scene is not yet on that ribbon. It waits for a specific ritual of timing, solvents, and light. When the ritual is performed, a latent trace becomes shareable. The film can be carried, compared, archived. No spirit needed, only a mark that endures. The mark is not decoration. The mark is what lets two different observers argue, test, and finally agree. Without marks, stories cannot be sorted by truth. With marks, stories can be made to stand trial. Suppose the universe is the kind of place where reality is exactly the totality of stable marks made by interactions. Suppose everything else, whatever we dream behind closed eyes, is prelude only. Then the question that rattles in the background of all physics takes a sharper edge. If no interaction leaves a mark, what does it mean to claim an event occurred? Is existence without record like a sentence without letters? Could such a thing be more than a preference in our heads? To move forward, we will not chant slogans. We will lift instruments that have proved their worth. Telescopes that compare the position of a star before and after it, threads the gravity near a luminous disk. Atomic clocks that taste height, speed, and rotation, and refuse to tick alike when those flavors differ. Radio baselines stretched across continents that time the whisper of a galaxy jet so precisely that geometry itself becomes visible. Phototubes lowered into reactor pools where a blue glow announces that charged particles outran light through water, but not through a vacuum. None of these are myths. Each is a machine for writing. You do not feel time bend when you look over a city from the hill, but a clock does. You do not sense a correction in your phone, as it takes signals from a ring of satellites. But the correction is there, shaving microseconds so that your map lines up with your shoes. The adjustments are small and relentless. Each adjustment is a nick in our naive picture. Each nick secretly confirms that the fabric beneath our feet is stitched with curvature and motion. We are not insulted by these corrections. We are oriented by them. Now return to those pairs of tiny spins flying away from a source in opposite directions. We twist our analyzers to orientations we choose after the pairs are already on their way. We record the joint results and compare. The numbers do not fit a world that assigns each particle a private script. The numbers fit something else. A script written in the pattern of pairs only when both sides are read. No signal leaps the gap faster than a flash. No violation of the critic that speed imposes. Yet the structure of the marks refuses to be parceled into local causes alone. Do we accept such a world? If we do, what becomes of the comforting idea that everything near you is only shaped by what is already here? A rumor often retold says that the three-dimensional world we know might be encoded on a surface of 2 dimensions, the way a relief engraving holds a scene. If that rumor is to be more than a metaphor, it must be hammered into consequences. If the number of bits needed to describe a region rises with area instead of volume, then gravity, heat, and information are not separate topics. They are faces of a single coin. Does our universe carry a surface that could serve as this ledger? Our universe appears to expand with a positive push near emptiness. Does such a universe admit a neat, distant wall? Or must the ledger be drawn in a different way? Local, patchy, provisional. In plain terms, we are asking how nature must be arranged so that our measurements can be compared and sewn into a single, shared story. We are not asking for mind over matter. We are asking for rules that guarantee that 2 honest experiments done in different places can be made to agree or disagree in ways we can predict. If space can curve, the rules for clocks must include that curvature, and we can test them. If certain joint outcomes exceed what any local script permits, our rules must admit that, and we can test them again with cleverer arrangements that close every loophole we can find. If a boundary ledger would rescue us from paradox, we must learn what counts as a boundary in a world like ours. Certainty will not accompany us at every step, but we can be clear about which stones are firm and which are still sliding. It is firm that starlight shifts when it passes near mass, with an angle that matches a curved geometry, not a straight one. It is firm that clocks diverge in rate when speed or height differs. It is firm that some correlations among separated systems cannot be reduced to private instructions assigned in advance. It is not firm that a global boundary holds all interior events the way a museum wall holds a map. It is not firm that gravity is only shape and not also a pattern emerging from microscopic accounts. It is not firm that our best picture is a simulation. And even if it were, the word simulation might be a way to talk about finite resources rather than a claim about authors. Look again at the eclipse plates stored in an archive drawer. Each star is a dot with a faint pencil circle and a neat number beside it, before and after the sun swam by. The dots live at slightly different coordinates against the gridded glass. The difference is small and decisive. It is a verdict written in silver and ink. In a different drawer, there are images from a radio array that watched a jet from the heart of another galaxy. The bright knot that seems to outrun light only does so in the way a beam spot can sweep faster than any runner across a distant wall. In a reactor pool, a blue halo blooms where charged fragments rush faster than light can manage in that medium, generating a shock of light. None of this threatens the rule that a pulse in vacuum sets the limit. All of it reveals how easy it is to mistake appearances for laws. A natural worry arises. If an outcome can depend on what can be known, why does a vast, unobserved wilderness not dissolve into nonsense? The answer is that observation in physics is not admiration. It is interaction that leaves a trace. Photons bounce from rock and water. Molecules collide and stick. Crystal lattices ring and settle. These are silent clerks stamping forms all day. You can leave the room. The clerks continue to work. The world does not wait for you to look. It waits for any process that can produce a stable record. Another worry sits close by. If gravity sculpts the roots through space and sets the rhythm of clocks, is time nothing but a trick of the path we take? Tricks do not grow tomatoes or age bones. Time is the bookkeeping we do to keep track of change. The books may be kept in different currencies depending on altitude and speed, but they still account for the same harvest and the same heartbeat. The differences tell us that geometry matters. They do not tell us that becoming is fake. Let us set our itinerary. First, we will walk straight into the measurement trap and see why a mark, once made, narrows the questions that remain meaningful. Next, we will examine the verdict that correlations can surpass any local script without letting messages outrun light. Then we will test the idea that a boundary can hold a volume and ask what kind of boundary our cosmos could possibly supply. After that, we will climb a ladder of clocks and show how time accounting depends on root and curvature. We will chase the mirages that seem to outrun light and learn how perspective, media, and geometry conspire to fool us and how deeper limits survive. We will meet gravity in its double form, as geometry and as a suspected emergent order, and we will weigh proposals that revise dynamics against maps that insist on unseen mass. Finally, we will consider the wager that our world is like a render that shows you only what you approach, and we will ask how such a limit would announce itself in data rather than in fiction. Along the way, we will ask small, sharp questions. What truly counts as a measurement? What is the minimum mark that makes a fact? How can a world stay causal when parts of it refuse to remain local in the way our habits prefer? If a ledger on a boundary is more than an image, what unit entries would it store? And how would those entries govern the life inside? If time is accounting rather than command, why does the account feel like a current that carries us one way only? If space can curve until straight becomes bent, what keeps the order of cause and effect from tearing apart? Here is a final image before we begin. A workshop at night. Glass plates labeled in pencil rest beside a metal lens that smells faintly of oil. A clock with a quiet second hand ticks on the wall. A shallow tray sits ready for a strip of film. The apparatus is not mystical. It is honest. It writes in a language that other hands can read. We will use rooms like this, and instruments like these, to climb out of slogans into statements that can turn out true or false. That is the only road to a reality we can share. That is the only respect we can pay to a universe that needs no permission to be what it is. If you are ready to trade conjecture for checks and balances, to map a corridor through paradox by measuring where its walls actually stand, then walk with us. The next doors will not open by poetry. They will open by patience and by the blunt courage to say what the marks allow and what they do not. We will begin with the measurement trap, the first gate that turns questions into answers or into errors. Enjoy clear, data-driven journeys. Like and subscribe to the Quiet Universe channel. Imagine a particle so small that it slips through your fingers of thought. You release it toward a pair of openings. You expect a dot on a screen, a small, obedient mark. Instead, the marks gather into stripes. Then you alter only one thing, a device that learns which slit each particle used, and the stripes melt into a fog. The universe has not changed its parts. The difference is in what could, in principle, be known. The experiment that began as a simple test of wave and particle becomes a riddle about existence itself. What does it mean to say something happened if the record depends on whether you ask the question? The measurement trap is not about carelessness. It is about the deep rule that outcomes and questions are not separable. Each instrument defines what can be said. The grain of reality we uncover is not pre-written in the thing. It is shaped by the way we touch it. In quantum theory, this rule is formalized with numbers and operators, but before it was an equation, it was a shock to reason. When you measure position, momentum blurs. When you measure momentum, position hides. It is not a flaw in the device. It is a statement about what the world can simultaneously reveal. There is a human analogy, simple and cruel. When you interview someone under a bright light, the pressure changes the answers. Ask a question too directly and the mind folds in on itself. The data you record are not false, they are conditioned. The same is true for electrons, photons, or atoms. A detector is an interrogator, and the answer depends on the intensity of the light in its face. Reality, at least at this scale, is conversational. We receive only the replies that our instruments allow. Early in the last century, this principle seemed tolerable. Confined to the small, we still believed that, at macroscopic scales, the world behaved like gears and pulleys, deterministic and serene. Then a physicist proposed a thought experiment involving a radioactive atom and a cat sealed in a box. The decay of the atom would trigger a vial of poison. Before opening the box, the theory said the atom had both decayed and not decayed, and the cat was both dead and alive. It was never meant to be literal cruelty. It was a mirror held up to absurdity. If measurement makes reality, where does that process stop? Does the act of human observation collapse the ambiguity, or does the universe itself perform the act as soon as the record becomes irreversible? That word, irreversible, is a lifeline. When a photon strikes a grain of photographic film, a molecule changes its shape. The energy cannot be undone without effort, and that effort leaves new traces of its own. Irreversibility is what elevates an event from whisper to testimony. The universe may tolerate superpositions and probabilities, but when an interaction becomes thermodynamically one way, it joins the set of facts. In plain terms, the world is generous with possibilities until a mark is made. Then it keeps the mark like a signature. This is not mysticism. It is bookkeeping. Measurement is the currency of that bookkeeping, and the ledgers are everywhere. The cosmic microwave background is a fossil of photons last scattered when the universe was young. Those photons carry the marks of density ripples frozen into a pattern of heat and cold. When we point a radio dish at that faint glow, we are reading a record made nearly 14 billion years ago. No mind recorded it, yet it persists, as if the universe were its own archivist. If the universe can record itself, why do we matter? Because our experiments compress that vast archival process into moments we can read. We build devices that force the abstract to leave tangible prints. When a quantum sensor emits a click, it is not conjuring reality from nothing. It is joining a chain of records that began before stars formed. Our role is not to cause the universe to exist. It is to compare the marks it already made and decide which pattern fits best. Consider another version of the trap, one that hides in statistics. A measurement is always an interaction between system and observer, but our records are aggregates of many such interactions. When we say a particle has a 50% chance of going left, we do not mean that it flips a coin each time. We mean that in a long series of similar experiments, half the marks end up left. The probability is a statement about information, not about hidden forces. If you think of it as ignorance, you may imagine a deeper truth waiting to be revealed. If you think of it as completeness, you realize there is no deeper layer. The map is the territory. To put it another way, probability is not a confession of failure, but a property of the world. When we speak of a wave function collapsing, we mean that one branch of possibility has been written into history. The others remain unrealized, like drafts abandoned in a notebook. The trap tempts us to imagine those drafts lurking somewhere, but physics gives no place for them to rest. The only reality is the one consistent set of marks that survive comparison. A paradox grows from this soil. If measurement creates the record, how can we trust past records that were never observed by us? The fossils in rock, the redshift of galaxies, the cooling of background radiation. All are evidence of processes we never witnessed. The solution lies again in the chain of irreversibility. Each layer of record is built upon previous ones, each interaction sealing its own proof. A trilobite pressed into shale is a mark of contact between shell and mud that did not need a viewer. The decay of uranium in the rock created helium bubbles we can count. Those bubbles are not waiting for our gaze. They are already written pages. A laboratory filled with sensors is a condensed history of such processes. A detector waits in silence. When a particle passes, the silence breaks into a pulse of current. That pulse becomes a bit stored in memory, a trace on a drive, a print on a sheet. Hours later, a scientist reviews the data and plots the results. The measurement chain is complete. At each step, the world became less reversible. At each step, information flowed from the uncertain to the fixed. The observer is only the last reader in a long series of scribes. What traps us is our language. We speak of observation as if it were passive, but in physics, it is an exchange. To observe is to trade energy and information. A photon that lets you see an object does not leave it untouched. It imparts momentum. However small, the act of knowing alters the known. The better our instruments, the subtler the disturbance, yet never zero. The dream of perfect knowledge without interference is a mirage. There is no divine surveyor standing outside the game. Yet all hope is not lost. The uncertainty that frustrates precision also safeguards coherence. Without it, atoms would collapse. Electrons would spiral into nuclei. The blurred boundaries of quantum behavior are the reason matter is stable. What limits us also allows us to exist. Why it matters is simple. The same rule that denies total certainty ensures that the stars do not implode into silence. Nature balances between knowability and survival. We have learned to make peace with this. In modern quantum optics, researchers can delay the decision about measurement until after a particle should have completed its journey. They find that the results still obey the same logic. The outcome depends on what could, in principle, be known. Not when the decision was made. Time does not rescue realism. The order of cause and effect stretches to the edge of sense. Our instruments obey a story that does not align with human intuition, yet never breaks its own arithmetic. Think of it like this. The world is a stage lit by spotlights of measurement. Only the lit parts have definite form. The darkness is not void. It is potential. When a spotlight moves, the old forms fade, but their imprints linger as geometry, as energy, as memory. In this way, measurement is both creation and erosion. It carves certainty from possibility and feeds uncertainty back into the void. Some wonder whether consciousness itself is the ultimate measuring device. The idea is seductive but risky. Experiments show that unconscious detectors, automatic counters, and even inanimate materials produce the same results. Awareness may not be required. What is required is interaction that leaves a record that resists erasure. Consciousness adds narrative, not necessity. The trap lies in confusing the reader with the ink. We can test this claim. If measurement required mind, the decay of distant radioactive atoms would wait for us to look. But detectors left running in sealed vaults record events regardless of attention. Cosmic rays strike emulsions on mountains. Neutrinos trigger flashes deep in Antarctic ice. Chemical reactions proceed in darkness. The universe does not consult our schedule. It measures itself continuously, converting uncertainty into history, one irreversible trace at a time. The philosophical sting remains. If everything is process and record, where is the boundary between the possible and the real? The answer, thin and practical, is that the boundary is wherever interference can no longer occur. Once paths lose the ability to overlap, reality has selected. The wave function is not destroyed. It is dispersed into the world. The pattern of possibilities becomes part of the environment, hidden in correlations too complex to retrieve. The result is what we call a fact. To see why this matters, consider the devices that run our lives. Every transistor in a computer works by steering electrons through potential barriers. The current that flows is predictable because the probabilities have stabilized. Each logic gate is a tiny act of measurement, a collapse of options into one path. Modern physics does not merely describe this. It enables it. Your phone, your car, your telescope are built on the controlled use of quantum decisions. Certainty within limits is the scaffold of technology. In every corner of our civilization, the measurement trap still waits. Economies depend on metrics, and those metrics shape what they claim to describe. Sensors guide climate models, and those models dictate where we build and how we farm. The feedback between observer and system is no longer a metaphor. It is a global force. Understanding its structure at the atomic level helps us manage it at the human scale. The lesson from the slit experiment applies to policy as much as to physics. The questions we choose determine the answers we will be able to live with. Our next step will turn this local paradox into a global challenge. When separate particles share correlations that defy local causes, the trap widens into a verdict about the structure of reality itself. The question shifts from how measurement defines an outcome to how distant outcomes conspire to stay connected. The path leads from the chamber of slits to the courtroom of entanglement, where nature will testify against the idea of locality. In the early hours of an experiment that would unsettle philosophy, two detectors sat in darkness 50 kilometers apart. Between them, a source emitted twin flashes of light. Each flash split into a pair of photons that flew in opposite directions. Nothing about either photon could be known until it struck its own detector. And yet when the results were compared, they showed a strange harmony. The outcomes were not random. They were linked. When one tilted left, the other tilted right. When one showed a certain polarization, the partner matched in a way that no local rule could predict. The effect was named entanglement, a word that sounds gentle but carries the gravity of a verdict against common sense. At first, many dismissed the correlation as a bookkeeping artifact. Maybe the photons carried hidden instructions, like twins separated at birth who still follow a private script. If each photon knew in advance how to respond to any future test, then no mystery remained. But the tests became more clever. Physicists varied the angles of their detectors after the photons were already in flight. They found that the correlations violated an inequality derived from any local script one could imagine. The data did not allow for hidden settings that merely waited to be read. Something deeper was binding the outcomes together. Something that ignored distance, yet respected the limit that no signal travels faster than light. A riddle now stood in the courtroom of physics, demanding judgment. The witness list was long. Einstein had once called entanglement spooky action at a distance, not as praise but as complaint. He believed that a proper theory would eventually replace the ghostly action with clear local causes. The experiments did not comply. The more they were refined, the more they insisted that locality, as we defined it, was not the whole story. To preserve realism, one had to sacrifice locality. To preserve locality, one had to give up the idea that properties exist before they are measured. Either way, something in our picture of the world would have to bend. Imagine two coins tossed far apart. Each lands heads or tails. If they show the same face half the time, we call that chance. If they match every time, we suspect a trick. Entanglement produces matches at a rate between chance and certainty, a rate precisely predicted by quantum theory. No wire connects the coins, no message passes between them, yet their outcomes fit a pattern that cannot arise from independent events. The implication is not that information flies faster than light, but that the joint system is a single object, no matter how far its pieces travel. The separation is spatial, not causal. The universe keeps their bookkeeping together in a way that transcends our partition of space. In plain terms, the universe seems to treat the pair as one event with two addresses. What happens at one end is not decided there alone. It is decided by the structure that spans them both. If we could see the world in the language of mathematics directly, we might find that distance is a convenience, not a boundary. Entanglement is a geometry of information, a curve that passes invisibly through the void, joining points without crossing space. The verdict arrived through statistics, not poetry, repeated trials with photons, electrons, even ions trapped in fields confirmed the same excess of correlation. The inequalities that local theories obey would cap the coincidences at a certain number. The data broke that cap again and again. Every loophole closed strengthened the case. Timing windows were narrowed so no signal could travel between detectors. Random generators chose measurement settings in real time. Some groups used starlight from opposite sides of the sky to pick detector angles, ensuring that even cosmic coincidence could not explain the pattern. The universe, impartial judge, continued to deliver the same verdict. A strange calm followed among the investigators. They had not destroyed causality. They had refined it. Cause and effect still ruled within each laboratory. But the story that connected both labs was not a sequence of signals. It was a tapestry of shared constraints. Each measurement result was like half of a sentence. Only when the two halves were read together did the meaning appear. Reality, it seemed, was a grammar, not a list of words. The human scale echo of this is familiar. Two musicians, playing on opposite sides of a canyon, can remain in tune even if the echoes between them are delayed. They rehearse not by signaling during the performance, but by sharing a common score beforehand. Entangled systems share no physical score written in advance, yet they behave as if the universe itself holds the sheet music. The melody remains synchronized without communication. This is why experiments that separate entangled partners by mountain ranges or orbit still produce harmony. The universe does not pass messages between them. It performs the duet as one. A skeptic might still ask, what if the detectors themselves influence the source retroactively, weaving a subtle conspiracy backward in time? Some have tested even that. In delayed choice experiments, the decision of what to measure is made only after the particles have left the source. The results are the same. The verdict holds. The pattern of correlations does not depend on the timing of our choices. It depends only on the network of possibilities that quantum law allows. Time, like space, is part of the fabric that the entangled system ignores when writing its own coherence. The mind reels at the consequence. If two events far apart can share a reality stronger than any classical connection, what defines individuality in a physical sense? Are separate things truly separate, or are they projections of a single deeper order? Some interpretations claim that entanglement proves the world is fundamentally holistic, that division is illusion. Others caution that such statements run ahead of the data. The one thing agreed upon is that locality, as once cherished, is not absolute. The lines we draw between here and there are useful, not sacred. A thought experiment can help. Imagine a pair of gloves packed in separate boxes. Send one to Mars and keep one on Earth. Open the local box, see a left glove, and you instantly know the other is right. No mystery there. The pairing was fixed before shipment. Entanglement is not like this. It is as if each glove exists in a cloud of possibilities until opened, and the moment you check one, both acquire definite chirality that fits together. There was no prior assignment. Yet no conflict arises. The rules of classical intuition are suspended. The gloves were not objects with labels. They were potentialities constrained by symmetry. Why it matters becomes clearer when we consider communication. Entanglement cannot be used to send messages faster than light, but it can reveal when a message could not have been tampered with. Quantum encryption depends on this property. Any attempt to eavesdrop changes the correlations in a detectable way. The very feature that confuses philosophy protects information in practice. Out of paradox comes utility. The uncertainty that once mocked certainty becomes a guardrail for truth. Another consequence lies in computation. Entangled bits, or qubits, can represent many possibilities at once. By allowing them to evolve together, a quantum computer explores multiple routes through a problem simultaneously. The results are read in the interference of those routes. Again, no signal outruns light, but the structure of shared possibility gives a new kind of leverage. Nature has shown us a pattern, and technology is learning its rhythm. Still, the philosophical charge cannot be discharged so easily. We like to think of the world as composed of parts whose behaviors add up to the whole. Entanglement says the whole determines the parts. The cat in the box was already a warning. Now we see that even distant experiments participate in joint realities. What does it mean for objectivity if every measurement is part of a larger, entangled web? Perhaps objectivity is not the absence of relation, but the presence of consistent relation. Reality is not a list of isolated facts. It is a network that must hang together without contradiction. In plain terms, the universe behaves as if all things are connected by a hidden accounting system. Each measurement updates the ledger in a way that keeps total balance. No debt of probability is ever left unpaid. We never see the ledger directly, but we infer its rules from the consistency of outcomes. Entanglement is the audit trail of that accounting, the evidence that the universe maintains coherence across all scales. Some thinkers reach for metaphor. They picture a great loom weaving space and time, with entanglement as the threads that cross the void, holding the pattern firm. Others prefer the imagery of music, where harmony arises from the relation of tones, not from the independence of instruments. Both metaphors touch the same insight. The universe seems less like a collection of objects and more like a collection of relationships. We must not romanticize this into mysticism. The data are sober. They do not tell us we create reality by thought. They tell us that reality, as described by experiment, is relational. Each fact owes its definition to context. There are no freestanding properties, only values that make sense within a pattern of measurement. Once that pattern is set, the results are as rigid as any law. Before it, the system is a web of potential. After it, a ledger of facts. The courtroom metaphor returns. On the stand, nature has given its testimony through entangled pairs. The verdict reads locality, as an absolute principle, is not upheld. Yet the speed limit of information remains enforced. The jury of experiments agrees. We live in a world where correlations outrun explanation, but not signal. The law of cause and effect survives. But its jurisdiction is smaller than we thought. The rest belongs to a subtler order where distance and separation are provisional. The implications reach beyond physics. In every network, from neurons to societies, relations matter more than isolated nodes. The quantum story may be extreme, but its lesson scales upward. No part of a system is truly free from the constraints of the whole. Cooperation, coherence, entanglement by another name, is the mechanism by which complexity persists. The void between things is less empty than we imagined. If the first chapter trapped us in the problem of measurement, this one sets us free to see connection as the missing half. We have learned that observation shapes outcome, and now we learn that outcomes themselves can be shared across space, as if distance were only a delay, not a wall. The next question will push these findings against the very boundary of the universe. If information binds distant particles, could it also bind the contents of all space to a surface that surrounds it? The next chapter will follow that hint into the idea of a holographic boundary where the whole cosmos might be written. Stand in front of a sheet of glass etched with a spiral of light. When a beam passes through, it recreates a three-dimensional image floating in air. You can move around it, see its depth, and yet there is nothing behind the glass but interference. The information of the whole picture is encoded across the surface. This familiar trick of holography becomes startling when we apply it to the cosmos. What if the entire universe works like that piece of glass? Each patch of space recording the pattern of what happens within, the inside written upon the outside. The idea sounds poetic, but it came not from poetry. It came from the mathematics of black holes. Decades ago, physicists studying black holes faced a paradox that threatened to break their laws. When matter falls into a black hole, its details disappear behind the event horizon, a region from which no signal can return. Yet the black hole still has temperature, entropy, and the ability to radiate slowly away. If information truly vanished, the fundamental rule of physics that evolution is reversible would fail. The cosmos would lose track of its own bookkeeping, searching for balance. Scientists discovered something peculiar: the entropy, the measure of missing information, scaled not with the volume inside the horizon, But with the area of the horizon itself, every bit of lost data was represented by a patch of surface. The boundary carried more meaning than the interior. In plain terms, the amount of information needed to describe everything that happens inside a region is proportional to the area of its boundary, not the space it encloses. This rule, extracted from the mathematics of gravity and thermodynamics, became known as the holographic principle. It says that reality as we experience it might be a projection from a distant surface. The bulk of space could be a translated version of data living on a lower dimensional frame. We are not watching shadows on a cave wall. We may be the three-dimensional expression of a two-dimensional ledger. The evidence for this idea began with black holes. But it soon spread. The same equations that describe gravity near a horizon also govern the dynamics of fluids and quantum fields. In certain simplified universes, especially those with a negative curvature known as anti-de Sitter space, researchers found an exact correspondence. Every field and interaction in the interior could be mirrored by a theory without gravity, living on the boundary. The two were not similar stories. They were the same story told in different languages. What was curved geometry on one side became quantum mechanics on the other. The translation was perfect. Every detail accounted for. Our own universe does not share the negative curvature of that toy model, but the hint is powerful. If such a duality can exist at all, it means that space-time and matter are not separate ingredients. They are two faces of one coin called information. Geometry might not be the foundation, but the consequence of how information is arranged. To walk through space could be to surf through a sea of correlations, each defining the distances between events the way pixels define depth on a holographic screen. The implications reach far beyond black holes. Consider the cosmic horizon, the spherical limit set by the age of the universe and the finite speed of light. We cannot see beyond it. Yet its area defines the largest possible entropy our observable patch can contain. The calculation echoes the black hole result. The visible cosmos could be the interior of its own boundary, a gigantic hologram projected inward. Every galaxy, every wave of radiation, every heartbeat could be part of an encoded display whose true storage lies at the edge of what we can see. It is tempting to imagine the boundary as a literal wall, a cosmic mirror carrying patterns of light. The truth is subtler. The boundary is not a place, but a mathematical surface that holds the limits of information flow. No traveler will collide with it. It is the sum of all possible messages that could ever reach us. The holographic rule tells us that those messages are enough to reconstruct everything within. If we could read that surface completely, we would have the full script of our observable universe, though written in a cipher we have yet to crack. Why it matters lies in the problem of gravity. Einstein's equations tell us how matter curves space-time and how curvature directs matter. But quantum theory demands that every degree of freedom, every possible state, be countable. If gravity's degrees of freedom live on boundaries, then space-time itself may emerge from entanglement patterns among those boundary bits. In that view, space is not fundamental. It is an illusion born from the way information knits together, where entanglement thins, space stretches. Where it thickens, space contracts. A hole in the fabric, such as a black hole, is where entanglement has collapsed almost entirely, leaving a region that the rest of the network cannot access. Imagine walking through a library where each book's spine is woven into the shelf, and the shelf itself forms the floor and ceiling. Every page you read alters the connections among the shelves, reshaping the room as you move. In such a library, space would not be a container but a product of relationships between words. The holographic universe is similar. The text of reality is stored not in the objects themselves but in the relations among them, projected from a boundary that keeps count of every possible story. Skepticism is healthy. The holographic principle remains a conjecture, not a proven law. Our universe's positive curvature, driven by dark energy, complicates the translation that works so well in anti-de Sitter space. No one has yet built a perfect duality for a cosmos like ours. But the success of the idea in describing black holes and the hints of it in quantum information theory make it more than speculation. It is a tool that keeps finding new use. It links thermodynamics, quantum entanglement, and geometry into a single language. It may one day tell us why space-time itself feels continuous even though its information content is finite. At its heart, the holographic principle rewrites what we mean by inside and outside. If all that occurs within a region can be represented on its boundary, then the concept of locality becomes porous. What you call your position in space may correspond to a pattern of information smeared across a distant screen. The notion sounds alien, yet our daily experience with data hints at it. A film, a map, a photograph, all store dimensional depth on a surface. You can reconstruct the shape of mountains from a contour map or the motion of a dancer from a sequence of flat images. The difference between illusion and reality may be one of scale and precision, not of kind. In plain terms, the holographic view tells us that the universe might not need more than 2 dimensions of information to describe 3 dimensions of experience. The extra depth could be the way those 2-dimensional data interact. This concept resonates with the lessons of entanglement. When distant particles share a single description, they act as if the space between them is irrelevant. Extend that logic to every part of the cosmos, and space itself could be the large-scale illusion of such connectivity. Still, a profound question remains. If the universe is a hologram, who or what performs the projection? The answer is that no one must. The projection is not an act, but a relation. The bulk and the boundary define each other simultaneously. Like 2 sides of a coin, neither exists without the other. There is no external projector. Only the structure of physics itself, weaving interior and exterior into one fabric of information. The idea can even recast the mystery of time. On the boundary, events might be static correlations, timeless data. Inside, those same correlations appear as evolution. As the passage from past to future, time would then be the way a 3-dimensional observer reads the frozen script of the boundary line by line. In that sense, history is not written after it happens. It happens because it is written. Why this matters to us is both technical and philosophical. Technically, the holographic principle offers a path toward quantum gravity, a theory that unites the small with the large. Philosophically, it invites humility. We live inside the image, unable to step outside and see the glass that holds us. Our telescopes reach farther. Our equations grow sharper. But every insight hints that the real structure of reality is thinner, more abstract, and more interconnected than intuition allows. A traveler who looked back at the night sky from the edge of the visible horizon would not see stars receding into darkness. They would see the faint shimmer of the boundary itself, a surface encoding all stories within. Somewhere in that lattice of light would be the pattern that corresponds to us thinking about it, a recursion as quiet as breath. If the entanglement of particles binds local events across space, could the entire universe be bound by a single sheet of information? The next step is to trace how this hidden geometry might generate the one thing we feel most personally yet understand the least, the flow of time itself. A clock on a mountaintop ticks faster than one at sea level. The difference is small, yet it is measurable. Lift an atomic clock by a single flight of stairs and its rhythm shifts. Carry it aboard a plane and it gains microseconds compared to its twin left on the ground. At first, this seems like a defect of the clock, an artifact of motion and altitude. But when every type of clock behaves the same way, we realize that it is not the device that is changing. It is time itself. Gravity and speed alter its pace, bending our private seconds into a larger geometry. Time, it turns out, keeps its books in ways that no single observer can audit completely. Einstein's theory of relativity taught us that time and space are part of a single fabric called space-time. Movement through one affects measurement in the other. The faster you move, the slower your own time flows relative to someone standing still. The deeper you sit in a gravitational well, the slower your clock runs compared to one higher up. These effects have been confirmed so precisely that our global navigation systems must correct for them every moment. Without that correction, the position on your phone would drift miles each day. Relativity is not an abstraction. It is the accountant behind every coordinate. Yet our everyday sense of time does not match this elasticity. We feel a single universal flow carrying all things forward. We plan by calendars and pulses, not by curved metrics. To reconcile the two, physicists built a new notion: proper time, the duration measured along a specific path through space-time. Each world line, as it is called, has its own measure. There is no master clock ticking for all. Instead, the universe allows each traveler to keep their own ledger, and those ledgers disagree in consistent, predictable ways. This is why twins parted by a high-speed journey age differently. The Voyager's path through space-time is longer in space and shorter in time. The reunion is not a paradox. It is an audit. In plain terms, time is not a river that flows the same for everyone. It is a network of paths whose rhythms depend on motion and gravity. Each path tells a coherent story, but those stories meet only at events where they cross. Outside those crossings, simultaneity has no absolute meaning. When we say two events happened at the same time, we are really declaring that light from them reaches us together. Another observer, moving differently, will draw different conclusions. The order of events can vary, though the causal structure, the sequence of what can influence what, remains protected. Cause precedes effect for all, even when their timing disagrees. This protection is what keeps the universe sensible. Nothing can travel faster than light, because light defines the slope of causality, the outermost boundary of possible influence. Inside that limit, signals and objects can interact. Beyond it, they remain forever out of reach. The finite speed of light is the firewall of history. It ensures that although perspectives differ, no observer can rewrite another's record. The Book of Time has many editions, but they all share the same spine. Why it matters becomes clear when we consider energy. In relativity, energy and mass are not merely connected. They are the same quantity in different currencies. The conversion factor is the square of light's speed. This constant binds the bookkeeping of motion and change. When energy is stored in motion, less remains for internal ticking. The particle's own clock slows. Its internal processes lag. The faster it goes, the more its time budget is spent on movement. When gravity takes hold, the curvature of space-time reshapes how light and clocks behave. The deeper the well, the fewer seconds per meter of climb. This is not illusion. It is the architecture of reality maintaining balance between motion, mass, and duration. Now picture a light beam climbing from the surface of a star. As it escapes, its wavelength stretches. The color reddens. The energy drops. To us, this appears as a gravitational redshift. But in another language, it is the same story told in time's currency. The ticking of light's waves slows as it climbs. Each crest reaches the observer later than it would in flat space. The signal records the gradient of time itself, carved into its frequency. When astronomers measure that shift, they are reading the slope of time in the gravity field. The red light from the edges of massive objects is a visible form of time dilation. If you travel to a region near a black hole, the slope becomes extreme. From far away, it looks as if anything approaching the horizon slows, freezes, and fades. From the traveler's own perspective, time continues normally, but their signals to the outside stretch infinitely. Communication stops. This is not because their own seconds vanish, but because the path for their information to escape becomes infinitely long. The horizon is less a wall than a financial barrier. Time debts cannot be repaid across it. The lesson of relativity is that time is not a passive backdrop. It responds to mass, to energy, to the presence of measurement itself. When you move, you spend part of your allowance on space and have less left for time. When you rest deep in gravity, you accumulate delay. The universe's ledger always balances. No motion, no clock, no signal violates the accounting. The invariance of the speed of light is the rule that keeps the sums consistent. In plain terms, think of space-time as a vast spreadsheet. Each cell contains the value of an event where and when it occurs. The entries are linked by formulas that ensure the total remains constant. Move a cell's position, and its time value adjusts to keep the product of light speed squared untouched. We perceive the sheet as flowing, but it is static in its completeness. Our movement through it is the act of reading row by row. Time's flow is our sequential perception of already balanced data. This static picture is known as the block universe, the idea that past, present, and future coexist in the full fabric of space-time. The sensation of passage is how beings like us experience slices of that fabric. The block view is controversial. It suggests that the future already exists, that our choices are coordinates, not creations. Many resist this conclusion. They point to the irreversibility of processes, to entropy, to the arrow of time as proof that the block cannot be complete. The argument continues. How can the whole four-dimensional structure be fixed if thermodynamics allows only one direction of increase in disorder? Entropy is the key witness in this debate. Every irreversible process, from melting ice to the decay of stars, leaves behind a trail of increased disorder. Entropy counts the number of microscopic ways a system can be arranged while still looking the same on the surface. The second law states that this count never decreases in a closed system. From this simple rule arises the arrow of time. We remember the past because it contains fewer possible states than the present. Memory is possible only when entropy grows. The block may hold all events, but within it, entropy marks a direction like a slope within a landscape. The river of becoming flows downhill along that gradient. In plain terms, the future is the region of higher entropy, the past, the region of lower. Our experience of time's flow is the brain's adaptation to that gradient. We sense the increasing disorder as progress, but the underlying laws, at the microscopic level, are reversible. If we could track every particle, the equations would run the same forward or backward. Only when we average over ignorance does direction appear. The arrow of time is statistical, not absolute, yet it governs every macroscopic phenomenon we know. Consider the universe itself. In its early moments, it was hot, dense, and smooth, low entropy despite its chaos. As it expanded, structure formed, galaxies coalesced, stars burned hydrogen into heavier elements, and entropy grew, black holes. Paradoxically, the most ordered objects in equations hold the highest entropy of all. Each adds vast entries to the cosmic ledger. The balance between order and disorder writes the story of cosmic time. When the expansion slows and matter decays, the ledger may approach uniformity again. A heat death, where no gradients remain, and time, as a measure of change, loses meaning. But before that distant quiet, time continues to evolve as a complex economy. Information can be lost from our view, but not from the total account. Hawking radiation, the faint glow from black holes, is one example of how the universe may settle its debts. Over eons, even the darkest objects evaporate, releasing bits of information in subtle correlations among their photons. The process is slow and uncertain, but it reassures us that the books remain balanced. Nothing of information is truly destroyed. It is redistributed. Our human sense of time rides atop this grand accounting. Each heartbeat, each orbit, is a local negotiation between order and entropy. The clock on your wrist measures a smooth progression because its mechanism is stable, but the thermodynamic reality beneath is restless. Even your memories are chemical states that slowly decay, rewritten each time they are recalled. The continuity we feel is an illusion of overlapping ledgers that agree long enough for life to persist. Why this matters is not only practical, but existential. Recognizing time as part of the fabric of energy and gravity shifts our view of mortality, of causation, of purpose. The future is not a blank page waiting for ink. It is a region we have not yet read. Our choices, our actions, are the paths that define which parts of the block we occupy. Freedom, then, is not the power to change the block, but the freedom to discover new coordinates within it. The next horizon lies at the intersection of time and motion. If clocks can differ, and time can stretch or slow, could geometry itself be bent to shorten distance without breaking causality? The following chapter will chase that possibility, following the dreams of warp and light bending into the mechanics of space itself, where the pursuit of speed reveals the deeper shape of the universe. Light has always been our measure of reality. It defines what can be seen, how distance is known, and how truth is timed. Every instrument in physics ultimately traces its scale back to light. Yet the more closely we pursue it, the stranger it becomes. It moves with a speed that no mass can reach, yet it yields to gravity as if it had weight. It can be bent, slowed in glass, or trapped entirely by the pull of a black hole. To chase light is to test the limits of space itself, for light and space are woven together, each shaping the other in ways that border on the impossible. Imagine standing near a calm lake before sunrise. You toss a pebble and watch circles ripple outward, perfectly even, their speed determined by the water. Light behaves in a similar way, except its water is space-time. The ripples move at one constant speed, regardless of how you throw the pebble or how fast you run beside it. This constancy, discovered through meticulous experiments, became the foundation of relativity. No matter how we chase it, light always slips ahead at the same pace. The result is not that light refuses to be caught, but that catching it would require turning space-time itself inside out. In the early 20th century, physicists dreamed of exceeding this barrier. They imagined particles or ships that might cheat by shortening the road rather than speeding along it. If you could bend the route between 2 points, perhaps you could arrive before light would on the unbent path. Gravity, in Einstein's equations, already does this. Massive objects curve space-time, changing the straightest paths, which are called geodesics. A beam passing near the sun bends by a small but measurable angle, the very effect that first confirmed general relativity. What was once invisible in mathematics became visible on photographic plates from an eclipse. The curvature of space was no metaphor. It was a tool for navigating reality. In plain terms, gravity does not pull light the way a hand pulls a rope. It changes the shape of the road that light follows. Light always travels straight. But straight has been redefined. Where the road curves inward, light's direction changes. And to an observer, it looks as though gravity is tugging. The same principle makes galaxies act as cosmic lenses, magnifying and distorting the light of distant ones behind them. Through these lenses, astronomers can map the hidden mass of the universe. The light from ancient galaxies becomes the probe of unseen gravity, showing how matter bends space and how space bends truth. As we chase light farther, we find that its speed is not merely a number, it is the conversion rate between space and time, the factor that sets how much of one can be traded for the other. When you move faster through space, you move slower through time. The total motion through space-time remains fixed, governed by light's pace. This is why no ship, no matter how powerful, can outrun light. The faster it tries, the more its own time slows, the more energy it requires to gain another fraction of speed, until the price becomes infinite. The universe enforces its limit not through walls, but through debt. Energy debt, time debt, curvature debt, all paths lead back to light. For decades, science fiction imagined breaking this rule with shortcuts through geometry wormholes, warp drives, folded space. Some of these ideas have mathematical forms. A wormhole, in the simplest picture, is a tunnel connecting two regions of space-time. The equations of general relativity allow such solutions, but they require matter with negative energy density to stay open. No such material has ever been found. Any normal matter would cause the throat to collapse faster than anything could pass through. The dream survives as an elegant sketch in the margins of physics, a reminder that equations can suggest more than nature permits. Warp concepts, in contrast, try to move a region of space-time itself. Instead of pushing a ship forward, you would compress space ahead and expand it behind. The craft would sit still relative to its local bubble, moving effectively faster than light relative to the distant stars without violating the local rule. The mathematics, first written down by Miguel Alcubierre in the 1990s, is self-consistent, but costly. The energy required is immense, and again includes regions of negative density. Some refinements reduce the burden, hinting that if space-time has elastic properties, there might be regimes where compression and expansion could mimic motion. For now, it remains speculative, a proof that geometry can, in principle, bend the notion of speed. Think of it like this. Light defines the boundary between what can be connected and what cannot. Within that boundary, space-time can flex. You can change the slope of the terrain, but you cannot leap off the map. The curves of gravity and the dreams of warp both exploit geometry. Yet neither escape the book of causality. The order of cause and effect remains intact. If the universe allowed true, faster-than-light travel, paradoxes would bloom effects preceding causes, messages arriving before they were sent, histories looping into themselves. The limit of light speed is the lock that keeps time from unraveling. The illusions of superluminal motion we do observe remind us that appearance and law differ. Jets of plasma streaming from the hearts of galaxies can seem to move faster than light when viewed from certain angles. In truth, they move near light speed, and their geometry tricks our perception. When a burst travels toward us at almost the same speed as its light, the time between emitted flashes compresses. The sequence of events piles up in our view, creating the false image of impossible speed. No rule is broken, but the lesson is clear: the universe is more cunning than our eyes. Cherenkov radiation offers another perspective. In water or glass, light slows because it interacts with the medium. A charged particle moving faster than light can move through that material, though still slower than light would move in vacuum. The result is a shockwave of blue glow, the optical equivalent of a sonic boom. It happens routinely in nuclear reactors, the water bathing the core lighting up with ghostly color. These moments do not overthrow relativity, they express it. The local rule remains sacred. Nothing outruns light in empty space. Why it matters goes beyond curiosity. Light's constancy is the scaffold of causality and information. Every signal we send, every observation we make, depends on knowing how long light takes to travel. Astronomers build timelines of cosmic history by measuring redshifts, the stretching of wavelengths as the universe expands. That stretching is the same story we met near gravity wells, but written on a cosmic scale. The farther a galaxy, the longer its light has traveled, the redder its hue. When we look across billions of light years, we look billions of years into the past. The night sky is a memory book written in photons. To chase light is to chase time itself. In plain terms, the speed of light connects everything. It sets the maximum rate at which cause can touch effect. It ties energy to mass. It even calibrates the rhythm of reality. Without it, equations would lose coherence, space would not know how to curve, and time would not know how to flow. Light is not merely what we see, it is what makes seeing possible. The cosmos uses it as both messenger and measure, weaving every event into a network of delays and arrivals. Still, curiosity drives us to push the boundary. We test whether constants have changed over eons, whether photons lose energy in subtle ways beyond redshift. So far, nature answers with silence. The constant remains constant. within limits ever tighter. Perhaps the ceiling of speed is not a prison, but an act of mercy. Without it, structure would dissolve, signals would overlap, and meaning would drown in simultaneity. As technology grows, we find new ways to bend light without breaking its rule. Gravitational lensing lets us peer into the deep past, magnifying galaxies that would otherwise be too faint. Adaptive optics reshape wavefronts to undo atmospheric blur. Quantum communication uses entanglement to synchronize keys without transmitting information faster than light, exploiting correlation instead of travel. Each method acknowledges the same principle: the path of light may bend, but the ledger of causality stays balanced. If time bends under gravity and light defines time's gradient, then understanding how space and light interact may reveal the hidden architecture of the universe. The curvature that guides beams also guides the expansion of the cosmos itself. Light's journey from the early fire to our telescopes carries the imprints of that expansion, a record of the shape of everything. To read those faint photons is to read the history of geometry written in motion. At the human scale, chasing light is a metaphor for pursuit of understanding. We can never overtake it, but every attempt teaches us more about the road. Each reflection, each refraction, each lensing arc tells us that space is not emptiness. It is the stage that both hides and reveals. To bend space is not to dominate it. It is to listen to its grammar. If the pursuit of light leads us to geometry, and geometry leads us to gravity's double face, then the next chapter must ask what that face conceals. Does gravity point to unseen matter, or does it hint that our equations are incomplete? The path ahead will compare these rival explanations, weighing dark matter against modified laws, to see which better maps the hidden mass of the universe. Gravity is the oldest force we know and the least understood. It keeps planets in their orbits, anchors oceans to Earth, and bends the paths of galaxies. Every child has felt its pull, yet its true nature remains divided between two faces. One face is the elegant geometry of general relativity, where mass and energy tell space-time how to curve, and curvature tells matter how to move. The other face is an invisible substance we cannot see, a shadow mass called dark matter that seems to tug where no known mass exists. Between these two views lies a quiet tension that defines modern cosmology. Is gravity a shape, or is it a symptom of something we have not yet seen? The story begins in the early 20th century, when Einstein's field equations replaced Newton's instantaneous pull with the idea that gravity is the curvature of space-time. Objects move along geodesics, the straightest paths through a curved landscape. Light itself follows these curves, revealing the geometry through bending and delay. For decades, this picture reigned supreme. It passed every local test with precision: the precession of Mercury's orbit, the deflection of starlight during an eclipse, the slowing of time near massive bodies, the subtle lensing of galaxies. Gravity seemed to be not a force at all, but a feature of existence. Then astronomers began to count. They measured how fast galaxies rotated and compared those speeds to the visible mass of stars and gas. The numbers refused to agree. Outer stars orbited too fast. In a purely Newtonian or relativistic framework, the rotation curves should fall with distance as the pull of gravity weakens, yet they stayed flat. Either every galaxy was surrounded by unseen mass, or the law itself changed at low acceleration. Two schools of thought emerged. One would fill the cosmos with dark matter, a halo of particles still undetected. The other would modify gravity's law, proposing new behavior at weak fields. Two faces, one mystery. In plain terms, dark matter acts as scaffolding. It provides the extra pull needed to hold galaxies together and clusters in place. Without it, galaxies would fly apart. Modified gravity theories, by contrast, argue that the apparent need for dark matter is an illusion caused by misapplying Newtonian intuition to cosmic scales. They introduce parameters or new fields that strengthen gravity when accelerations are tiny, replicating the observed rotation curves without adding invisible matter. Both explanations can be tuned to fit data, but each carries its own cost. Dark matter, the more conventional approach, fits beautifully into large-scale structure. Simulations that include it reproduce the web of filaments and voids seen in galaxy surveys. The gravitational glue of dark matter seeds the formation of galaxies and dictates how clusters merge. Yet direct detection experiments have come up empty. Decades of underground detectors and collider searches have not found a particle that matches the necessary properties. The invisible scaffolding remains inferred, not seen. Gravity's first face whispers that space is curved by what exists, but dark matter asks us to believe in what does not appear. Modified Newtonian dynamics, or MONDY, and its later relativistic cousins like TeVis, take a different route. They claim that at accelerations below a certain threshold, gravity behaves differently. The strength of the pull does not decline as quickly with distance. This simple rule reproduces the flat rotation curves with remarkable accuracy using only the visible mass. It predicts a consistent relation between stellar mass and rotation speed, now observed in hundreds of galaxies. But when MOND faces clusters of galaxies or the cosmic microwave background, it falters. The missing mass there seems too great to be explained by mere adjustment of law. Its elegance is local, not universal. The truth may lie between these views. Some theorists propose that dark matter could be more complex than imagined, perhaps interacting with itself, creating structures that mimic modified gravity at small scales. Others explore emergent gravity, where the curvature of space-time arises from statistical properties of microscopic degrees of freedom, much as temperature arises from molecules. In that picture, gravity is not fundamental, but emergent, a bookkeeping rule for the entropy of information woven into space-time. If so, dark matter might be the visible trace of hidden informational structure rather than literal particles. Gravity's two faces could then be reflections in a single mirror, one geometric, one thermodynamic. Imagine space-time as a stretched fabric of information, where data is dense, curvature deepens. Where it thins, space relaxes. Entropy, energy, and information flow together to define the shape. The force we call gravity would then be the universe's tendency to maximize entropy, pulling matter toward states with more accessible configurations. Galaxies would cling together, not because of invisible glue, but because the overall information balance demands it. In this view, dark matter is an effective field describing that tendency, the shadow of collective behavior, rather than a population of unseen particles. Experiments continue to test these ideas. Gravitational lensing, the bending of light by mass, offers a direct map of where gravity acts. When astronomers observe clusters like the Bullet cluster, they find that the lensing mass does not coincide with the hot gas seen in X-rays. The mass seems displaced, matching where dark matter would drift if it interacts weakly. This evidence favors the existence of an unseen component rather than a modified law. Yet other systems blur the line. In some dwarf galaxies, the correlation between visible matter and gravity's strength matches the predictions of MONDY better than those of dark matter halos. The cosmos appears to alternate between the two faces, as if choosing which mask to wear. Why it matters extends beyond cosmic bookkeeping. Gravity, in its essence, connects local experience to universal law. If we misread its structure, our picture of the universe's fate may be wrong. A universe dominated by dark matter and dark energy will expand forever, its galaxies drifting apart until only cold light remains. A universe where gravity changes at low acceleration could behave differently, perhaps slowing or cycling in unexpected ways. The choice between these faces determines not only how we model the past, but how we imagine the end. In plain terms, think of gravity as both map and terrain. One face describes the smooth curves that tell matter how to move. The other accounts for the missing mass that shapes those curves. Whether the map is complete or the terrain is richer than we see, we cannot yet tell. We test each with new measurements lensing surveys, precise pulsar timings, the dance of stars around black holes. Each test adds a number to gravity's ledger, narrowing the range of possible truths. What we find will decide whether the cosmos is mostly empty but well-curved, or filled with unseen matter moving in silence. Some physicists suspect that the division between geometry and matter is artificial. In quantum field theory, particles are excitations of fields. Perhaps gravity's field, too, can fluctuate in ways that mimic matter. A graviton condensate, if it exists, could account for extra gravitational pull without requiring new particles. In this sense, gravity could wear its own shadow, generating the illusion of added mass. The two faces would then merge, geometry masquerading as matter in regions of weak curvature. At human scale, gravity's duality appears only as comfort. It holds our feet to the floor and shapes the motion of tides. But even here, its subtlety shows. The Earth bulges slightly at the equator because rotation counters the pull. Satellites circle by constantly falling around the planet, experiencing near weightlessness in perpetual descent. Astronauts orbiting Earth are caught in this balance, both bound and free. The feeling mirrors our intellectual state suspended between understanding and ignorance, orbiting the truth but never landing. The philosophical echo of gravity's two faces is humility. We live inside equations that describe curvature and energy, yet we do not know what either truly is. Whether space curves because of matter, or matter arranges itself because of entropy's drive. Both statements capture part of the truth. Our task is not to choose which face to worship, but to find the deeper unity that wears them both. If the hidden mass of the cosmos and the bending of space are aspects of one phenomenon, then perhaps the final key lies in how information itself shapes reality. The next step will move from gravity's ledger to the most audacious speculation of all the possibility that the entire universe is a computed process, a rendering built from finite information. The following chapter will test that wager, asking what evidence might betray a simulated world hidden beneath the texture of space-time itself. Imagine walking through a digital landscape so finely rendered that even the dust motes scatter light correctly. Every shadow curls with physical logic. Every echo obeys geometry. You would not know, from within, that it was code. Reality, after all, is only what resists imagination. The simulation hypothesis begins from this observation and then multiplies it to cosmic scale. If consciousness can arise from computation, and computation can emulate physical law, then perhaps our universe is itself an emulation. This idea is not born from fiction alone. It is a modern restatement of an ancient question: how can we tell the difference between appearance and foundation? The wager is not that someone built the cosmos as a game, but that the rules we study may be the architecture of information itself. The first hints came not from philosophy but from physics. Every time scientists push deeper into matter, they find discreteness. Energy comes in quanta, charge in fixed units, spin in half steps, space itself possibly in finite grains according to theories of quantum gravity. The continuum of classical thought keeps breaking into pixels. If space-time has a minimum length and time has a minimum tick, then the universe may not be analog but digital. A program that updates its state step by step could explain why nothing moves faster than light, why uncertainty limits measurement, and why vacuum fluctuations appear as random noise in every experiment. The texture of reality could be the clock cycle of a cosmic processor. In plain terms, the simulation idea says that the universe is not continuous but computed. Every event is the output of an algorithm that follows consistent laws. The program does not need to exist on any physical computer we can imagine. It is enough that its rules produce the phenomena we call space, time, and matter. The appeal of this view is that it unites physics and information. Energy and entropy become not just metaphors, but literal measures of information processing. The laws of thermodynamics read like the documentation of a system maintaining its own stability. Critics object that such reasoning confuses model with maker. If physics can be described by computation, it does not mean it is computation. A map may have pixels, but the terrain does not. Yet the counterpoint is subtle. When equations describe all measurable behavior and predict the next state with perfect reliability, the difference between description and substrate loses meaning. The universe, by every operational test, behaves as if it is running code. Supporters of the hypothesis argue from probability. If intelligent civilizations ever learned to simulate conscious minds, they could produce vast numbers of virtual beings compared to real biological ones. Each simulated observer would perceive a physical world consistent with the program's laws. Statistically, the majority of conscious experiences would then occur in simulations rather than in the original physical world. By that logic, it is more likely that we are simulated than not. The argument is unsettling but not easily dismissed. Others turn the wager around. Suppose the universe is fundamental and finite, governed by immutable constants, then it must conserve energy and information perfectly. Any attempt to compute inside it must obey the same restrictions. No simulated world could match its fidelity because each level of simulation would demand resources greater than the level above. Therefore, if we can build stable, self-consistent virtual realities ourselves, it implies that our own world already possesses computational depth far beyond what we can simulate. Either we are at the top of the hierarchy or inside an infinite stack of emulations. Both possibilities force humility. There are, however, physical ways to test aspects of the idea. If reality is discrete, then at extremely high energies or fine scales, we might detect anisotropies, small directional preferences caused by the lattice of spacetime cells. Cosmic rays arriving from distant galaxies could betray such irregularities. So far, none have been found. Another proposal searches for the limit of precision in quantum mechanics. If there is a smallest time step, the spectrum of noise and vacuum fluctuations should cut off sharply beyond a certain frequency. Experiments have not yet seen this ceiling. The absence of evidence is not proof of continuity, but it pushes the resolution higher. If the simulation exists, it runs at a scale beyond our current reach. A more subtle test lies in information itself. In every physical interaction, the total amount of information is conserved, though it can be scrambled. Black hole thermodynamics, quantum entanglement, and the holographic principle all point to a universe that behaves like a perfect databank. No bit is lost, only hidden. This preservation echoes the way a computer simulation must maintain state across frames. Each update of the world must depend only on the previous one, never skipping information. The parallel is striking. The cosmos processes itself in logical steps, each cause giving rise to exact effect, just as lines of code execute instruction by instruction. Yet, the simulation wager carries danger. It tempts fatalism. If we are simulated, why strive? Why hope? But a simulation does not abolish meaning. The characters in a story still suffer, love, and learn. Their reality is internal to the narrative. If consciousness emerges from consistent information patterns, then those patterns matter wherever they appear. To exist is to participate in the computation, whether on silicon, in neurons, or in the structure of spacetime itself. The ethical question remains the same. What do we choose within the rules given? Think of it like this when we design virtual worlds. We encode physics for stability and beauty. We limit energy to prevent chaos. We impose boundaries for coherence. We allow freedom within constraints. The result can host emergent behavior far richer than the code implies. If intelligence arises there, it will read its own laws as we read ours. From its perspective, the equations will be real. We, its creators, would seem like distant gods, unreachable, perhaps mythical. The simulation wager mirrors this hierarchy. It suggests that we, too, might live in a realm whose architects are indifferent or absent, or that creation itself is recursive with no origin at all. Why it matters goes beyond metaphysics. The language of simulation helps physics translate mysteries into computation. Quantum mechanics, for instance, is naturally simulated using algorithms that track probabilities rather than trajectories. Quantum computers already exploit this parallel, processing information through superposition and entanglement. In that sense, they are experiments in mimicking the universe's own logic. When we build such machines, we may not be copying the cosmos. We may be conversing with it in its native tongue. Some theorists push further, proposing that consciousness itself is the universe reflecting on its own code. In this interpretation, the observer effect in quantum mechanics is not a quirk, but a hint that awareness is part of the system's feedback loop. The act of measurement updates the state of the simulation. While intriguing, this merges physics with philosophy. It cannot yet be tested, but it resonates with the idea that existence is a dynamic record of observation and response. Whether mind is the processor or the process, both share the same medium information. The wager has a long lineage. Philosophers once imagined the world as dream or shadow. Plato's cave, Descartes' demon, Leibniz's monads. All are attempts to grasp why perception feels more fragile than law. The simulation hypothesis is their digital descendant. It replaces mysticism with mathematics. Yet the question is unchanged: what, if anything, lies beyond the image? Perhaps nothing. Perhaps the image is all there is, infinite and self-referential, a program that writes itself forever. In plain terms, if the universe behaves as if it computes, then asking who runs it is less important than asking how consistent its computation can remain. Every experiment we perform is a query into that consistency. The fact that the laws hold, that constants stay constant, that chaos never overwhelms order, is evidence of remarkable stability. Whether that stability comes from an external coder or from intrinsic logic, it is the same miracle by another name. Skeptics remind us that even if the simulation idea is unfalsifiable, it can still be useful as metaphor. It forces us to think of energy as information, of entropy as forgotten data, of evolution as optimization. It frames the search for unification as the search for a single algorithm that generates both quantum mechanics and gravity. In this light, physics itself becomes reverse engineering, not worship, but decoding. Ultimately, the wager is not about discovering a hidden computer humming behind the stars. It is about recognizing that the universe's precision might have limits set by information capacity. Space, time, and energy could be the emergent phenomena of a deeper logic, one that trades bits instead of atoms. We may never step outside to verify the architecture, but we can map its syntax from within. If all we have explored so far, measurement, entanglement, geometry, time, gravity, and the hint of simulation, points toward information as the root of existence, then the journey must end where meaning begins. The final act will step beyond science into reflection, asking what it means to live in a cosmos that may be conscious of itself. In the end, every experiment becomes a mirror. We build instruments to measure the universe, and the readings reflect ourselves back through numbers and light. From the double slit to the black hole horizon, from the clock on a hill to the detector that watches paired photons. Each device has whispered the same idea in different tongues. Reality is not a thing we hold. It is a dialogue we participate in. We are not outside looking in. We are inside looking deeper into the same fabric that shapes both observer and observed. The more precise our view, the more we see our own participation woven into the picture. The journey began with questions that seemed mechanical. What determines a particle's path? What curve does light take near mass? What counts as measurement? Yet those questions led us to paradoxes where nature answered with riddles. The wave is a particle only when you ask it to be. Time slows, not because clocks tire, but because motion and gravity reshape what we call duration. Gravity itself might be geometry, or memory, or both. When the dust settles, what remains is not a catalog of equations, but a pattern of relationships. The universe does not reveal its nouns. It reveals its verbs. In plain terms, existence may be less about what things are and more about how they interact. We cannot speak of mass without curvature, of observation without record, of information without change. These pairs are inseparable. Each defines the other. Like melody and rhythm, they cannot exist in isolation. This is why every field of science, when followed to its foundation, becomes philosophy. It must ask not only what happens, but what it means to happen. There is a quiet symmetry across all scales. The particle's uncertainty echoes the galaxy's vastness. Both express limits on what can be known. Entanglement links distant events, while gravity binds the near and the massive. The two faces of the cosmos meet in a single gesture connection. Information is never local for long. It flows through light, through curvature, through time, through awareness itself. The fabric that holds the universe together is not matter, it is coherence. And coherence, fragile and finite, is what we experience as reality. Think of consciousness as the faint shimmer that occurs when information becomes self-referential, a detector reading its own trace, a system that can model its own changes. In that light, the universe is not indifferent, it is reflective. Every atom, every thought, is a note in a feedback loop where energy becomes structure, and structure gives rise to awareness. Whether or not awareness is fundamental, it is certainly inevitable. The emergent property of a cosmos that computes itself into being. We live suspended between the measurable and the meaningful. The measurable assures us that laws are constant, that predictions hold, that we can trust the language of mathematics. The meaningful reminds us that those laws, though cold in symbol, describe the warmth of stars, the growth of minds, the passing of time. To know one without the other is to mistake the formula for the song. The universe sings not to please us, but through us, using every act of perception as a note. The holographic principle suggests that our world could be a projection from a boundary of information. If that is true, then everything we do is written twice, once in matter, once in code. The physical and the abstract coexist. Even our memories are echoes of that duplication. Patterns carved into neural tissue that mirror the pattern of experience. When we love, fear, or wonder, the same logic unfolds information, compresses into meaning. Perhaps that is the true engine of existence, the conversion of data into significance. Time's strange accounting teaches humility. The flow we feel as future rushing into past may be the brain's way of organizing entropic change. Yet that illusion is precious. It gives story to the static, purpose to the pattern. Even if all moments coexist in the block of space-time, the sequence of awareness we call living still matters. The record we leave, our traces, our art, our questions, becomes part of the universe's ledger. We cannot step outside the book, but we can choose how to write within its pages. In plain terms, we are the method by which the cosmos keeps track of itself. Our instruments are extensions of its curiosity. Our equations are its memory taking form. To ask what is real is to ask what the universe can verify about itself. We are that verification, the part of the whole capable of self-examination. When starlight bends through a telescope and strikes a sensor, the circle closes the universe, measuring its own curvature through the eyes of one of its outcomes. Every discovery adds a new layer of wonder. Entanglement reveals that separation is contextual. Gravity shows that emptiness has shape. The holographic view hints that surfaces know more than volumes. Even the simulation idea, daring though it is, reminds us that law and logic are powerful enough to produce worlds. The cosmos appears less like an accident and more like a sustained computation of possibility, testing every configuration it can. Life is one of those configurations, a temporary coherence that reads the code from within. Still, wonder must walk hand in hand with responsibility. If reality is relational, then meaning depends on how we participate. To observe is to change. To measure is to influence. Our technological reach already bends light, manipulates time signals, entangles particles across continents. Each act of measurement extends the conversation between matter and mind. What will we ask next? And what will our questions do to the world that answers them? Why it matters goes beyond knowledge. The quest to understand the universe is also the quest to understand ourselves. When we test the limits of light, we test the limits of perception. When we trace gravity's curve, we trace the outline of empathy, the invisible force that binds lives into shared motion. When we explore time's flexibility, we explore patience and memory. Science and philosophy are not opposites. They are mirror images, one mapping what is outside, the other mapping what it means inside. At its core, the search for truth is an act of hope. It assumes that coherence exists, that questions have answers even when they remain unreachable. Each generation inherits that hope, refines it, and passes it forward. We may never find the final theory, but we can keep refining our understanding until the distance between fact and meaning grows infinitesimal. The process itself is sacred, not because it ends, but because it continues. Look outward one last time. The night sky is full of ancient light, traveling since before there were eyes to see it. Some of it bends around invisible masses. Some is redshifted by expansion. Some is scattered by dust. Each photon carries the signature of its journey, a tiny record of geometry and time. When it reaches our instruments, we decode its message. It says that the universe remembers. It says that every event, no matter how brief, leaves an imprint somewhere. Nothing is truly lost. The silence between stars is not emptiness, but potential, waiting for translation. Perhaps that is the final echo. The universe is not a static thing, but a question asking itself, over and over, through us. The stars are punctuation, the galaxies clauses, and consciousness, the line break where meaning breathes. If reality is a conversation, then our role is to keep it honest, to listen deeply, to reply with awe. The cosmos has written itself into form, and now it pauses, waiting for the next question. What story will we ask it to tell next?